Good morning. So I'd like to start by thank you for inviting me to be here today. I've always felt like an outsider at OFC. I've been here a couple of times before, gave a couple of embarrassing talks that I might tell you about later. But I've always watched from afar with some awe and great deal of respect, because the people in the room here, you have created what makes the internet possible. The transmission systems, the switching systems, the optical switches, the TDM switches that really underlie the internet. And without that, that would not be possible. So I take my hat off to you, if I had a hat, and I thank you, and I'm really honored to be here. So according to the slide behind me, it appears that I'm going to be talking about software-defined networking. Well, actually, I'm going to be talking about something else. Really, what I'm going to be talking about is what allows us to think about ideas that challenge old assumptions, of which software-defined networking is one. Because as scientists and engineers, we are well trained to understand the foundations of what we do, to understand the boundaries of what we know, and even to be receptive in our hearts and minds to new ideas that push back those boundaries. So in conferences, in universities, in R&D labs, we're very good at debating and thinking about and mulling over new ideas that come along. And I think the history of innovation bears that out. But what we're not so good at, and I include myself in this, is opening our hearts and minds to ideas that challenge old assumptions, that cut right to the foundations of what we believe to be true. And this is very relevant in the topic of software-defined networking because it's not a particularly new idea, but it challenges an old assumption. And so when people challenge our assumptions, many of us have the same effect. We go red in the face. We kind of get a little bit cross and angry and emotional, and we feel as though a raw nerve has been touched. As researchers, we tend to close ranks and say, uh-oh, we can't bear to think of that idea that challenges the foundations of what we're assuming. And as industries, we tend to erect big walls to protect against this invasion of ideas that cuts away and risks and puts our big profit margins at risk, and there are big profit margins at stake here. So when it comes down to it, the success or failure of Sdn really is about protectionism and protection of current existing ideas. But let me put that to aside for one moment. I'm going to be giving you a talk today that's in 3 parts. I want to keep you on your toes, so I'm not going to tell you what parts 2 and 3 are yet. But I thought I would start by telling you a little bit about what I do. Just set a little bit of context. Let me tell you about why I love my job. So I'm a professor at a research university, and the thing that I really love most about my job is I get to work with people much smarter than me. My students, my colleagues, I don't say this out of a false sense of humility, but if it wasn't for them, if it wasn't for the ideas that they have, I certainly wouldn't be standing here. Many of the things that we've worked on, almost all of them have come from the opportunity to work with extremely smart people. Like all of you, I imagine, I love to work on intellectually interesting ideas, ideas that are intellectually interesting in their own right. For me, that's an essential part of what makes engineering fun. The engineer comes from the same word as ingenious and ingenuity, and thinking about intellectually interesting ideas is part of what makes it fun. But what I get most excited about is those ideas that might positively change the practice. And you might be thinking, what is an academic from the ivory tower doing standing here saying that they want to affect the practice and change and improve the practice? You don't see much of that going on, perhaps. But what gets me excited in the mornings when I'm thinking about what I'm going to do in the day is the thrill of making the internet or networks better, of actually affecting and changing the practice. In fact, I think it's kind of a responsibility as an engineering researcher. It's a vocational field like business law and medicine, that if we're not doing research that improves the practice, then what service are we providing to society as a whole? But the thing that really is fun about the freedom and independence of working in a university is then we actually get to try and change the practice. So I don't claim that this particular approach is the right way. It's just the way that's worked for me and for researchers and grad students who might be in the room. I just want to encourage you to think whether this would work for you in terms of trying to actually go about changing the practice. Because we tend to think of academics as writing papers. And then moving on and leaving others to figure out what to do. But really, my approach is to do whatever it takes. Prove a theorem, write a paper, build a demo, talk to lots of people in industry, write a standard, give talks, write a blog, start a company, build an open source tool, really whatever it takes that is particular to the topic that we're studying. The way I go about choosing research projects is, as you might imagine, the first and foremost test of a research project is pick a problem that's intellectually interesting. The second thing is it needs to improve the practice. I have to believe that it'll improve the practice. The third factor is a little less obvious. It's important to me that industry doesn't like it yet. About 10 years ago, I made a deal with my PhD students. About 3 to 6 months into a new project, we would go and talk to people in Silicon Valley, and we're very lucky to have them right on our doorstep. And we would go and talk to people at chip vendors, at network equipment vendors, and tell them about what we were doing. And the deal I had with my students is, if they really liked the idea, then we would immediately cancel the project. So why is that? Well, the rationale is, if they really like it, then they should be doing it. It obviously matters to their business. They have way more resources and way more people than I could ever muster. And so they should actually be doing the work. It's clearly too short term. The interesting problems are ones for which they say, huh? Or they roll their eyes and think, what are these people talking about? The really interesting ones are the ones that they hate. The ones that touch a raw nerve, that make them very uncomfortable and squirm. Of course, they may be doing that because it's a really bad idea. So we have to go away and figure out whether we continue to work on it. A good example that was very relevant to what I'm going to be talking about today is back in 2007, Martin Casado was a graduate student in my group, and Martin, Scott Schenker from Berkeley, and I were thinking about what would happen with a project called ethane. Ethane is really a precursor to the field of Sdn. So as you may know, ethane was proposed as a way to build enterprise networks. Rather than log into every switch to configure it manually, which is what happens today, the control plane is logically centralized, lifted up and out of the forwarding plane. The operator would create a policy indicating what they would like to have happen in their network. So for example, at Stanford, we identified 137 policies that actually identify the things that you can do in the network. And then the forwarding rules are compiled directly from those policies. So they are pushed into the switches and the forwarding plane directly so that you know that it does what you want. We built a prototype that had about 300 users back in 2007. And we were wondering, so what does this mean? It would be great if we could use this idea to affect the practice. So we went to talk to a few of our friends. Now, it was about software. So not surprisingly, one day we went to see Microsoft and said, come on in, this is great. We love the idea of software definition of networking. So I became a bit suspicious. If they like the idea, then maybe it's not such a good one. But I was thrilled to find that when we went to Cisco the next day, they said, this will never work. There were 50 people in the room, 50 of the brightest minds on enterprise switching, data center switching, and Martin gave a great talk about ethane. During the talk, the audience got redder and redder, angrier and angrier. At one point, they were yelling that this would never work. They tried it, it wasn't possible. One of the executives in the room even bet his house that this wouldn't work. We've got to call him on that one day. Not one person in the room agreed with us. This was great, because out in the parking lot, we looked at each other and we said, we must be onto something. We hit a raw nerve. It was the best validation that we could have asked for. So there's a checklist. It must be intellectually interesting, it must improve the practice, and industry doesn't like it yet. Of course, there's a tongue-in-cheek here. I don't claim to have the great wisdom to be able to see over the horizon. It's that we just get to sit in our lab, we get to sit in our houses and think about what will come. We don't have to worry about what we're going to do in the next 2 or 3 years. We don't have to worry about that bottom line. And really, we're looking for that balance between ideas that will have a relevance in 3 to 4 years that are going to be just out of sight of what people are doing today. Okay. So there's an interesting corollary of this, which is that often you just can't give stuff away. If you've seen people come in from academia and tell you about ideas, often you'll find that it's very tempting to dismiss those ideas as, well, it can't possibly work. It's coming from the ivory tower. What do these people know? Right, so first example, my first experience of this was back in 1997, building routers that were, designing routers and switching chips that were for routers that were at least an order of magnitude faster than anything that had been created at that point. We tried to give it away for free, went to many places. We found that industry wasn't ready, so we had to start a company. And there's a little bit of a pattern here, which is in about 2001, one of my PhD students was working on something that's now called network memory, which is memories optimized for packet switches and routers. We tried to give it away. We showed that they would save about $500 million per year in SRAMs. Industry wasn't ready, so we started a company, NEMO, which stood for network memory. And then something similar happened in 2007, the story of ethane. We tried to give it away for free. It was the early stages of Sdn. Industry wasn't ready, so we started Nicira. Another thing that I've done, which may kind of come as a little bit of a surprise, it's actually extremely common at Stanford. Stanford is very generous, and it allows the faculty to make the decision as to whether something is put in the public domain or not. So I put everything in the public domain. I have done so since 1999. Industry. The story is a little bit different. You invest huge amounts to develop and sell products. Those patents protect ideas and give people the confidence to invest. I really believe that university research should serve society at large through helping industry. We should stay ahead by running fast, not by protecting ideas. By putting things into the public domain, it makes it much easier to work with industry. And if it's good research, as I've said before, industry probably doesn't see it yet anyway, so there's not much to worry about there. So I've put everything in the public domain since 1999. Okay, enough of what I do. Let me move on to part 2, which is to tell you a little bit about software-defined networking. So what I want to do is to peel away a little bit of the hype, and no, maybe a lot of the hype that you hear about software-defined networking, and talk a little bit about what it is and what it isn't. And then I'll tell you a little bit about some of the technical consequences, and my guesses, my estimates of what some of the business consequences will be. So if you're in any doubt today about whether OpenFlow and Sdn will actually be deployed in the WAN, I really strongly, highly encourage you to look at this video. It's on YouTube. This is Urs Hurzel from Google. He's responsible for all of their infrastructure, their data centers, their networks. And he gave a talk describing how they started deploying OpenFlow into their wide area network a little over a year ago, starting from January of 2012. By the time he gave this talk in April, they'd been running it for 4 months. And he gave a very nice description of why they'd done that, what the benefits that they were seeing, and how within 4 months they were on 4 major revisions of the entire system, the software, because they owned it, they controlled it, they wrote it, they could actually move much, much faster than they'd been able to in the past. And this was a big benefit for them. But the history of software-defined networks really comes from this guy, Martin Casado, from when he was a PhD student at Stanford. So, what is Sdn when we clear away all the hype? Well, it's actually pretty simple. Sdn is the separation of the control plane from the forwarding plane. That's it. There's not really anything else to Sdn. Everything else that we hear about comes as a consequence of this. Either the attempt to define the interface that makes this possible, OpenFlow, or if something else comes along in the future. And the business consequences all come from that separation. And when people feel challenged and threatened and their protectionist tendencies come out, it's because of that threat to the vertically integrated industry that we have today. But I need to apologize to all of you because you already knew this, right? Because in the optical world, in the transport world, it's been like that forever, right? It's been like this for a long time. In fact, you might be thinking, geez, these packet guys are a bit slow. We've known this for decades. And you're right. But I want to impress something upon you today, and that is this. It's not that the separation is the end. The separation is the beginning. SDN is allowing the packet world to embrace modern software practices. And that is actually the surprisingly big benefit. So much has happened in the software world in the last decade that has been off limits to networking because they're closed embedded systems, that now that the software gets to run on general servers in data centers running modern software, it really allows people to use their imagination and rethink how networks are built. It also means an end to network protocols, but I'll come back to that later. So what is software-defined networking? You may have seen pictures that look like this before. Packet forwarding at the bottom, they would be the switches, whether they're Ethernet switches, routers, MPLS switches. They could even be TDM switches or WDM switches. And then a network operating system, which itself is a distributed system. I don't want you to go away with the impression that this is one box. It is a distributed system of servers, but that its job is to control the packet forwarding elements through an abstract forwarding model, so an abstraction of what forwarding is. And OpenFlow is an example, probably the most widely used at the moment, but any abstract forwarding model would be sufficient. What the network operating system is doing is providing a global network map, right? A consistent view of the current state of the network. So what links are up and down, what boxes are up and down, maybe who's connected, and provides that map to control programs that sit on top. And control programs could be routing algorithms, they could be policies, they could be access control, they could be firewalls, they could be entire cloud management systems that sit on top and exploit this. And really that control program is a function of the map. It sees the map, it doesn't see all of the goop that's below. That's all abstracted away from it, as in any good abstract model. It just sees that high-level map, and then it operates on it and performs a function on it. So what are the technical benefits of this approach? The first one is there is a well-defined control abstraction. In other words, the control of the entire system, the entire network, has been abstracted away into this creation of this map. So this control plane can run on modern servers. It can adopt modern software engineering practices. It's much easier to add new control programs, either by creating your own, or as a vendor supplying more in a modular way, or go and get an open source one, or go and get it from a third party. So it changes that nature of that business. Or you can just customize locally by getting rid of all of the features and functions that you don't need and reducing the complexity of the system to just those that you do. So in other words, instead of the thousands of protocols and features that come on a system, you can say, I just want to customize locally to the 5 that I use, so that it allows my network to be more reliable, and that makes it easier to manage. But really, the main technical benefit that comes is a refactoring through this modularization, which is a little different from how it's been in the past. And I'll show you what this means in a moment by way of an example. But with software-defined networking, we get to solve the distributed systems problem once, rather than for every protocol. Building distributed systems in software is really, really hard. But over the last 10 or 20 years, there have been many, many examples coming from cloud computing and large data centers on how to do this, great improvements on how to do that. And going back and looking at what happens in networking, every protocol solves its own distributed systems problem, and then confuses and argues and interacts with all of the other distributed systems, the other protocols running on the boxes, in order to create the correct forwarding state in the network. Let me show you an example here. Imagine on a router with some specialized hardware, we won't worry about what the switching is right now, has an operating system, and then let's say it's running OSPF, the Open Shortest Path First routing mechanism. What OSPF has as sort of the basic building blocks is it builds a network map by exchanging hello messages and building the link state of the network in order to build a topology. And then on top, it runs Dijkstra's shortest path first algorithm. So if I teach a networking class, I tell my students that OSPF is Dijkstra's algorithm. I kind of forget to tell them about the other part. But when you actually look under the covers, 95% of the code, 95% of the pages in the standard are about building the distributed system, the network map underneath, to build that state, that global map of the network. And then the algorithm is just a couple of pages. That's the easy part. It's the intellectually interesting part, but it's the part that is actually very small in practice. In an SDN world, how this looks is we have the network operating system to build us that global network map, and so the control program just needs to implement the algorithm upon that map. So this is true whether it's OSPF, whether it's a firewall implementing a policy with access control lists, or whether it's BGP or any other mechanism like that. And I'll show you a specific example related to GMPLS later. The second technical benefit is the well-defined forwarding abstraction. And as I've said before, OpenFlow is an example of this. It's a vendor-agnostic interface to the forwarding plane. It makes the hardware potentially simpler, lower cost, and lower power, because now it has a well-defined role rather than having that tendency for features and functionality to creep down into the hardware. Really, all OpenFlow is doing is providing this abstraction, which is of match plus action forwarding. What do I mean by that? Packets arrive. Doesn't matter whether it's an Ethernet packet, an IPv4, IPv6, an MPLS, doesn't matter what it is. It has a header and it has some data. When that packet arrives, we have a table on the switch, and that header is used to index into that table to find a match. And if there is a match, an exact match Ethernet address or an IP prefix, something like that, then there is an action associated with it that tells us what to do with the packet, how to process it. That might involve modifying the header. It tells us which port or ports to send it out of, and then it goes on its way. So those action primitives are where all the interesting stuff lies. The matching is fairly straightforward. It might be SRAM-based exact matching with hashing. It might be TCAMs, whatever makes sense for the particular application. The action primitives, or I like to think of them as the plumbing primitives, are the things that are telling us how to forward the packets and how to process them. It might say, the action for this packet is forward it to ports 4 and 5, or push a little bit of extra header after a certain number of bits, pop a header and remove it, decrement a few bits that represent a counter or a time to live field, or drop a packet. So very simple operations. So you can see where this is going. There's essentially a small instruction set, a very small instruction set, that tells us how to process packets, and we can build up out of this set of instructions the processing for any individual packet. So what has this done? This has abstracted away the protocol underneath. What it's saying is, you know, Ethernet, IP, IPv6, MPLS, they're all really the same. We perform a match, and then we perform an action. This is just saying, this gives us a way to treat them all the same and hide many of those details where they're unnecessary. Now, most boxes will work with a whole suite of protocols. And those protocols generally like to have their own tables. And so there's a slightly easier abstraction, which is one consisting of multiple tables. And we just call this multiple table match action, where a packet coming in, it might have several headers corresponding to different protocol fields. We might use the first one to look up in the first table, and then the second one to look up in the second table with some metadata that comes from the first. And so that would all be in the purely forward pipeline of the box before the packet eventually goes on its way. So that's really it. There's not an awful lot more to it apart from the configuration of the box in order to make it work in the first place. And really the philosophy behind this is long-term, forward-looking. The goal is a match which is as general as you can make, that is not protocol specific. Right? So allowing as general as possible. An action set which is small, a small compact instruction set, like the RISC instruction set for a CPU, that's not protocol specific either, that allows you to build what you need for protocol processing. So to make it easy to add new headers, new actions for any network or whatever its type. But in order to get there, we need to go through the pragmatism of saying, how do we make that work today on chips that exist today, on hardware that exists today? And that's what really the last 3 or 4 years have been about. It's been going through and making sure that you can include well-known fields that exist today for protocols at layer 2, layer 3, layer 4 that people use commonly today. And figuring out the necessary action set for the existing protocols. And then figure out how you support this in existing switch chips. So for those of you familiar with what's usually called OpenFlow version 1.0, that really is in the bottom category. It's how do you make it work with existing stuff. OpenFlow 1.3 is about halfway between the bottom and the top, between the short term and the long term. And over time, we want to move much more to the more general, forward-looking way that will make it much more flexible as a much more general abstraction. And towards this end, there's a whole category of new switching chips that are emerging. Several startups, Intel is now in the field as well. Chips that will try and support in a more general way, and this is just showing one example of a pipeline. This is a chip that was designed by TI, but there's a number of them coming along in various flavors. These chips will be reconfigured or reprogrammed in the field in order to be able to support new protocol formats under the control of the control program. So as the control program evolves and changes, it will change the way in which it uses the hardware, just like a program will change the way in which it uses a CPU. So for example, if a data center operator wants to add a new field for encapsulation and aggregation for a new tunneling format that may be private within their data center, they could easily do that just by merely telling or configuring the switch with a new parse graph in order to allow it to parse that, and then telling it how it matches and then how it forms the actions. So as you might expect, packets would come in, their header would be put through a pipeline as a sequence of matches plus actions which are implementing those plumbing primitives as it goes through, recombined with its data, queued, and then goes on its way. And it's going to be quite an interesting competitive field of these OpenFlow optimized switching chips, and we can expect to see switching chips with in excess of 2 terabits per second of switching capacity in the next couple of years. So the third technical benefit is the well-defined forwarding behavior. So I just said well-defined forwarding abstraction. Now I'm going to say well-defined forwarding behavior. Some interesting consequences come from this. So the forwarding tables capture the entire forwarding behavior of the system. The control plane writes that forwarding state. Therefore, we can verify its correctness. If we wrote it, rather than it being built by a set of protocols that are all operating in some distributed independent way, if we are the control program and we wrote that forwarding state, then we can check whether it's correct, whether we can check whether the behavior of the network matches our original intent and the policy that we had in mind. What I mean by this is, in the software-defined networking world, you have a control program. This is a very crude firewall program. That program would be operating on that map, and then it would be compiled down into forwarding rules that would be placed into the switches, those match plus action tables in all of the switches. So if we look at what can go wrong here, there are really 3 places that things can go wrong. The first one is we might write a bad program. The second thing is the software infrastructure might be wrong. And the third thing is that the contents of those tables or the way that they're executed is incorrect. So now we can isolate the places that things can go wrong. I'm missing out the links here, of course, but just on the logical forwarding state of the system. This is not unlike the chain that goes through from a program through an operating system, a compiler on a computer, and there are many, many existing software engineering techniques for checking the correctness of the behavior. So if you think about what happens in networks today, we check network correctness using traceroute and ping. That's about all that we have. And then in the underlying layer, we have the OEM primitives. But it's a pretty rudimentary field. Software engineering and chip design are way, way ahead of us on this. And so what we're trying to do is to figure out how we can more formally verify the correct behavior of the network. So for example, if we look at those entries as they're being pushed down into the forwarding tables, that's the forwarding state that determines the behavior of the network, then we can look at the policy that we had in mind. Things like A can talk to B, guests can't access patient records, there should be no loops. And then we can compare it against the forwarding behavior represented by those forwarding rules. So we can do a comparison of those if we can formally capture that forwarding behavior of the network. It's very difficult to do in an existing network because it's so complicated, but now we've simplified and abstracted it because it becomes much easier. Because networks today are notoriously hard to debug and to verify. Even simple questions are very hard to answer. If you go to a network administrator and say, can host A talk to host B? They can't tell you unless they actually go to A and ping B. What are all the packets the packet headers that A could send that could reach B? There is no system that's deployed today that will tell you that. So it's basically, if you want to know how could A infiltrate B, you need to know the answer to this. Are there any loops in the network? Is group X provably isolated from group Y? Are the group of people who shouldn't be able to see the credit card transactions actually isolated from the credit card system in my environment? What happens if I remove a line in a configuration file? This is something that people fear greatly. Someone has left, an administrator has gone and worked for a competitor, and now, or they've retired, and now you want to remove or change a configuration. You don't know what's going to happen. So how could you figure this out? So there's something that we developed. This is going to be the only technical part of the talk over the last few years, called header space analysis. And rather than necessarily being the perfect answer, it gives you an indication of the sorts of things that are possible, and you'll start to see things like this emerge over the next few years. So imagine that you have a network like this, A and B interconnected by a very simple topology. In header space analysis, we represent a packet by its header and data, and we're going to be interested in the header because that's what determines the forwarding behavior of the network. So we're going to assume that all packet headers are less than L bits long, where L is just the length of the longest header in the network, and that really represents a point in an L-dimensional space. Right? So this is only 3 dimensions because we can't picture L dimensions, and so this is a point. This packet represents a point. As that packet goes through the network from A to B, it gets transformed by the routers. Maybe the header gets changed, and it gets forwarded. And so it will get moved to some other point in that L-dimensional space as it goes through the network. So we can capture the behavior of boxes by the way that they not only process individual packets as a transformation, but how they transform regions. Those regions could correspond to IP prefixes, or all the port 80 traffic, or all the traffic coming from the CEO. And so the switches and routers really are just performing geometric transformations on these regions. That's it. So if we know what the transformation is, we know the contents of the table, then we can build this transformation. And once we build that geometric transformation, then we can ask questions of it and perform an analysis using the tools that we all know. So for example, if we wanted to ask the question, tell me the set of all packets from A that can reach B, we can represent each of the boxes in the network by the transformation. The contents of their forwarding tables, basically, that tells us how they transform those regions. We can perform the thought experiment of saying, what if we were to put in the entire region across all L dimensions, in other words, the all wildcard, right from the beginning, the set of all packets, right? And then see what happens to them as they go through the network. Well, some of them will be filtered, some of them will be sent to different links. And if we follow through the network, through these transformations, we can get to the endpoint where we can figure out the regions the sets of the regions that can possibly get to B. This tells us all the possible packets that could arrive at B. There are no others. It doesn't tell us which ones we can send to get to B. We don't know that yet. We actually have to invert this. It's a geometric map, so it's invertible, so we can work our way backwards and then say, what is it that could have reached this region just by performing the inverse transfer function of each box and going back to the beginning? And now we know that those two purple regions there are the set of all possible headers that A could send that could reach B. Once you know the forwarding behavior of the network, you can do this directly, extremely quickly. For example, last summer, one of my students, Payman Kazemian, who came up with this method, spent the summer at Google and performed this on their OpenFlow WAN, which is their entire backbone network, and was able to perform policy checks by performing this analysis in less than 1 millisecond every time there was a change in their network. So every time there was a change in their network, they could perform a complete policy check according to all the policies that they intended. That's something that you definitely couldn't come close to today. So the consequences are a sort of an abstract forwarding model that's protocol independent that can prove that two groups are isolated and can verify if a network adheres to its policy. And we think of this header space analysis as sort of a foundation. We think there are many, many other things that you can do with it for things like dynamic testing, automatic test packet generation, automatic performance monitoring, and we think that there will be many, many things here. And if you squint, you'll see that there's an analogy here to Boolean algebra for logic design. It's creating something that's very similar, and you end up with truth tables and Carnot maps and all of this kind of thing that we're familiar with, and really that's the stage that we're at today. We don't yet have all of the advanced tools to apply. So we think there's a lot of headroom there over the next few years. Okay, what are the business consequences of Sdn? Well, first of all, vertical integration will actually be replaced by a more competitive industry with a level playing field. Let me explain why that is in a moment. We will see a large growth in a software industry for networking. We don't really have one today. This will lead to faster innovation. We will see hardware switches that will focus on capacity, fan-out, and power rather than on cramming more features into the hardware. All of these are good. All of these are good. And I do believe that there will be a multi-billion-dollar tools industry that will grow up around networking in order to support it based on the methods that I've just described. Perhaps more importantly, as a corollary, the customer and the end user will be better served this way. Networks will be cheaper. Networks will be faster. Networks will be much, much more reliable. They'll improve faster. Networks will be in the service of the owner, the operator, the customer, and the application rather than just the high-margin vendor. I actually believe that Sdn is in the best interest of society at large, which is why I am personally interested in continuing to work on it. And I wanted to explain this by way of an analogy. You may have seen this analogy before. It's a bit of a cheap shot at IBM, I'm afraid, but if you look back to the 1980s and think what happened in the computer industry, we had a vertically integrated, closed proprietary industry for which we were all told that if you're buying a computer, buy it from us, and we will provide you the specialized hardware, the specialized operating system, and all the applications, because we know best, we can make it all work together. Right? That was the mainframe mentality of the 1980s, and it worked well for a while. But then what happened was the microprocessor came along with a well-defined instruction set and an open interface. It had to be open in order to program, which made it possible to have many operating systems, and we see many today, lots of competition and innovation that takes place there, and then applications that sit on top. So an industry that was vertically integrated and relatively small grew and exploded into a horizontalized industry with open interfaces and much more rapid innovation. So what's happening in the networking industry? Well, today we're in a situation of specialized hardware, specialized control plane, and specialized features. We're in the mainframe era still, and that industry is vertically integrated, but what's happening is merchant switching chips from companies like Broadcom, Marvell, Intel, et cetera, and Mellanox that are producing chips with more open interfaces. They're a little bit hid behind NDAs and SDKs today, but that's gradually opening up, and that's really what OpenFlow is doing. Once we have open interfaces, you will see a variety of different control planes. I could list about 12 different OpenFlow control planes today, some of them closed, some of them open, that are going to compete in the marketplace on top of this interface. So rapid innovation taking place here, and then control programs or apps that will sit on top. So an industry that's vertically integrated and closed will become, over the next few years, horizontalized and open. And this picture, this analogy, I think is the one that captures most accurately what's going to happen as the business consequence and why it's really in the best interest of all of us, everyone, including the existing networking equipment vendors. Because today's routers have to support hundreds of protocols, thousands of RFCs running on tens of millions of lines of code and are beginning to look kind of outdated. And I would just want to impress upon you one piece of fear, uncertainty, and doubt that will be sort of perpetrated and passed around over the next few years. I want to tell you what Sdn isn't, and that's ramming in even more lines of code to an already complex system. You will see this happen. You will see vendors suggest this approach, that really all it means is my box now has an OpenFlow interface too, which is taking an already complex system and making it even more complex still. So resist that when you see it. That is not Sdn. OK, part 3, briefly. I already said that you guys know this whole thing already, which is the separation of control from forwarding and the programmatic control of forwarding by writing entries into tables. That's what transport networks are. That's what they've been for a long time. Transport networks have done this for decades. Okay. So there is a natural evolution. There is a natural evolution here towards converged control. It's been talked about for a long time. I don't think I say this naively. I know there's been a huge amount of effort in this direction. We all know it's where we should end up in the interests of the capital expense and the operational expense of people who operate networks. That today, and I use as an example here, data centers interconnected by an MPLS network, that there is a growing tendency for that network operating system to control the MPLS layer, but then in the middle is a massive transport network, which is controlled by the operator and controlled quite differently using different schemes, proprietary schemes. And what I actually believe will happen, it will take a while, is that eventually this will be subsumed into the network-wide operating system as this comes together. So you imagine a company like Verizon with multiple data centers interconnected by its own network. It is natural for these things to come together and for that distributed control plane to operate as one. It'll either be through the direct control of hardware, in some cases, or the control of a virtual transport network provided by the underlying operator who gives a logical view of a transport network under the control of the customer. I think we will see both. And in fact, there's a new Open Networking Foundation working group just established this past week to work on optical transport directly for this purpose. And I encourage you, if you're interested, to take part in that. So what else will happen? Well, the match action forwarding abstraction, as I described before, fits very well with packet flows, where you can use something like OpenFlow to control the plumbing, the way that those flows get directed. But it's pretty much the same if you're doing something which is packet in, circuit out. So something that is mapping Ethernet flows into circuits. You need a table in order to map it into the circuits. So the circuit is really just a logical output as far as the table is concerned. And you can control it using OpenFlow. And there have been many examples of this today. Saurav Das, who was one of my PhD students, had demonstrated this working in collaboration with Ciena and with Fujitsu over the last few years. And you could also use it, of course, for just controlling the cross-connect table in a TDM or a WDM cross-connect using just OpenFlow. And we will see extensions of OpenFlow to do it. So this is the most obvious way and the simple way in which you'll see Sdn come to transport. And this is a good thing. It's allowing the transport devices to differentiate themselves on what they are best at, while allowing the control to be in the distributed control plane and move and improve as it will. It's a little scary to think about from a business point of view, but ultimately, this is in the best interest of the customer and the best interest of society at large, so it will happen. One thing that I would hope would happen is that it will finally make possible that dream of many of dynamic circuit switching or dynamic provisioning available to the customer. The first talk I gave at OFC about 10 years ago, I predicted that dynamic circuit switching would actually replace core routers within 10 years. So 10 years is today, and it hasn't happened, so maybe I should eat my hat. But I do believe that what was supposed to happen, which was this transport network that would gradually push out and be the core to which the packet networks would connect through a UNI, for example, that has been long in coming. And the reason it's supposed to happen is the much higher capacity of optical cross-connects. So it's a much more efficient way to provide capacity. It provides aggregation, so those high-speed packet networks today are heavily aggregated, heavily smoothed, and so you can do dynamic circuit provisioning and serve them very, very well. It should be more cost-effective because circuit switches cost much less. I always tell my students, if you want to build a circuit switch, start with a packet switch and then throw away about 85%. And that's when you end up with a circuit switch. They're much lower power, they're much higher capacity, they're much lower cost per bit per second, and they use much less power. And there was a standard that was emerging called GMPLS that was supposed to solve this. And here is the problem, right? It didn't happen. I believe that all three of the first things were right, and the fourth one was wrong. And the reason that it was wrong was because it was building on top of all the complexity that already existed. There was an unwillingness to go back and say, how should it be done right? For good reason, I understand, but that was where the mistake was. It allowed the router vendors to prevent it from happening because it was threatening to them, and the GMPLS standard had to become much, much too complicated. I want to give you an example, finish with an example of why that was too complicated. And this came from Saurav Das, who was a PhD student, who was looking at this question of why is this unified and this converged control of networks, why does it look as though it's going to be so complicated? And that was really because packet networks on the left, controlled by control planes that are pushed down into the forwarding elements. So the operating system and those millions of lines of code sit on every forwarding element. Yet on the transport network side, we have the vendor-specific islands and their proprietary interface to the EMS. The IP MPLS control plane on the left, based on OSPF-TE and RSVP-TE, and many, many, many more things. And on the right, there was an addition of GMPLS control plane, right? So all of this complexity then communicating over this UNI, we really, really didn't make it very easy at all. So let's take a look at the complexity here. So we were kind of curious to know, really at the end of the day, you're trying to do very simple operations. What you're trying to do is things such as aggregation, dynamic bandwidth, automatic recovery. That's what you want of the transport network. So the number of lines of code that we looked at from an open source implementation of all of this was about 175,000 lines of code that would sit on the IP or GMPLS side in order to be able to perform this function. And so then we re-implemented it in software and said, what would it take if we were to perform that aggregation, that dynamic bandwidth, and that recovery, same functions, same features, protocol, the same, compliant and compatible. And we build it on top of an open source, open flow control plane called Nox, which has about the same number of lines of code as Quagga. And it took 4,000 lines of code. So just to compare here, 4,000 or 5,000 compared to 175,000. Same functions, compatible. It's 3% of the code. Why is that? It's because good architecture simplifies. If you go back to the basic, rethink of the modularity, the interfaces, the APIs that you need, it really simplifies. Not only is it less code, it's therefore more reliable, easier to maintain, easier to improve in future. So by going back to really what we need, control planes that control a bunch of networks, and then writing those control programs on top, we make the network much simpler. So let me conclude by saying the following. Sdn is here to stay. It introduces the right abstractions into network control. It will sweep away many protectionist practices and level the playing field. It's going to enable converged control of packet and transport networks. I really believe that. It may take 10, 15 years to do so. There's a lot of things to change. And personally, I don't recommend sitting on the sidelines. Thank you. if you'll give me one more minute, I want to send you something that somebody sent to me after I gave my last talk, and it was this picture here, to capture this change. And so here's the networking situation as it is today. So really what's going on here is there's a wedge being driven between the control plane and the control programs that goes on, and a wedge being driven between the hardware and the networking operating system to leave us this model here. And this is the mental model that I wanted to leave you with. Thank you.